Hey, it's your favorite Algebra 2 student, and today's lesson is 3.6 linear systems in three variables. And so far, we've been solving systems of equations with two variables, x and y, and finding the solution, which is where the lines intersect on the coordinate plane. Now we're solving system of equations with three variables, x, y, and z, and finding their solutions in a 3D coordinate plane.
Exactly. And so now we've got three dimensions here. We have an x-axis, a y-axis, which is what we're normally used to. But now we also have this z-axis, and this kind of pops straight out of the page right at you. The best way we can draw it is kind of drawing this angled axis like this, because we can't, physically draw it popping out of the page like that. But when we graph these linear systems in three variables, we have to imagine we're graphing three planes. All right. Remember, a plane is just a shape with width and length, but it has no depth to it. And so if we graph these three planes, where these three lines, as you can see in problem one, we got these three different planes here. We're looking at where they intersect. And there's three different scenarios. The one scenario is if these three planes intersect at a single point. So there is one unique solution. When you graph your solution in two variables, you get x comma y. Now we're using three variables. Your answer is going to look like x comma y comma z. So instead of an ordered pair, you have what's called an ordered triple, where x is the first number, y is the second number, and z is the third number. You could also have a scenario where the planes have no solution, right? These three planes intersect at 1, 2, 3 unique places, and there's no place where all three of these planes have in common. The last possibility is if you have infinite solutions, and this would be the scenario where all three of your planes intersect at a single line. And so they have this infinite number of solutions because, again, a line is made up of an infinite number of points. All right, so there are three different possibilities here. The ones that we're going to do in this example pertain to mostly this first example here, where there's one unique solution, x, y, z, but it could be one of the other two scenarios where there's no solution or infinite solutions. So all we're asking for in number one is 5, negative 2, 3 a solution to the system? So we know what they're asking is is x equal to 5, y equal to negative 2, and z equal to 3. So all you're going to do is you're going to plug in 5 for x, negative 2 for y, and 3 for z in every one of these equations. So if we look at the first one, we've got 2 times 5 plus 4 times negative 2 minus 3 times 3 equals negative 7. And if we simplify this, we get 10 minus 8 minus 9 equals negative 7. And then that ends up as being negative 7 equals negative 7. All right, so that is a true statement. It works for the first one. Let's try the second one. We have 3 times 5 minus a negative 2 plus z is 3 equals 20. So we get 15 plus 2 plus 3 equals 20. And it is, in fact, true that 20 equals 20. So that's also true. And the last one, x is equal to 5 plus 2 times negative 2 minus z is 3 equals negative 2. So 5 minus 4 minus 3 is negative 2. And this is going to be true as well. All right. 5 minus 4 is 1. 1 minus 3 is negative 2. So because this ordered triple works for all three of my equations, we know that this is going to be a solution to the system. So our answer to this is going to be yes. All right, this is a solution. So now we're going to do problem 2 here, and now we're actually going to be asked to solve. Notice this is the exact same system of equations here. You can look back at example number 1, it's the exact same. So we know already that my answer should be 5, negative 2, and 3, right? We know this should be the answer because we just verified that above. But I'm going to show you how to actually solve this if we weren't already aware of the answer. The first step into solving this is to pick the variable that is easiest to eliminate, right? Pick the variable that's easiest to eliminate. And that's kind of personal judgment here. I look at the x's, and those wouldn't be too hard to eliminate, right? I could imagine multiplying this bottom equation by negative 3 to get these to cancel. And then I could also imagine multiplying maybe by negative 2 on the bottom, because then these would cancel here. So you're always trying to look for whatever's going to be easiest for you. And again, a lot of times it's personal preference. You might do it different than a classmate who might do it different than I. But again, it's all just kind of what you feel would be easiest. So when I look at this system of 3, I might think that eliminating z's is going to be easiest, all right? So what I'm gonna do for step 1 is I'm choosing to eliminate the variable z, all right? That's my step z. So we're gonna use elimination, we're in step 2 now. Use elimination twice to get rid of that variable. The result should be a system of 2 linear equations in 2 variables. So what I can do is I can pick any 2 of these equations. So I could pick the first and the third, I could pick the first and the second, or I could pick the second and the third. You get to pick any 2 of these 3 combinations. Now again, what I'm doing is I'm choosing this wisely so that when I pick my, my 2 equations, I'm going to have the least amount of work to do. So I'm going to start by picking equations 1 and 2. Equations 2 and 3 here. Those are the ones I want to start with here. So we're going to take the 3x minus y plus z equals 20. And we're going to take the x plus 2y minus z equals negative 2. All right, so I'm choosing the second and the third equations to work with. Now, luckily, the plus z and the minus z are always going to cancel out. So I can just add these together using elimination. And now we get 4x plus y equals 18. All right, so this is one of my linear equations in 2 variables, right? We have no more z's, we just have x and y. Now what I'm going to do is I'm going to pick 2 other equations, all right? Again, I want it to be kind of easy to eliminate the letter z. So I'm going to pick the first and the second ones, all right? And I notice that right now the z's would not eliminate. So what I'm going to have to do is I'm going to have to multiply this second equation by positive 3. So we're going to take that 2x plus 4y minus 3z equals negative 7. And we're going to take this 3x minus y plus z equals 20. And just like we did with elimination before, we're going to try to eliminate these. So I'm going to multiply everything by 3. That's going to give me 2x plus 4y minus 3z equals negative 7. And 9x minus 3y plus 3z equals 60. All right? Now I can use elimination because we see we have these opposite coefficients. So when I add these, we get 11x plus y equals 53. And again, notice I have no more letter z's in that second equation there. And now that I have these 2 equations, now we can go about our normal solving systems of linear equations in 2 variables. So I'm going to line these up. I'm going to take my 4x plus y equals 18, and I'm going to take my 11x plus y equals 53. And as it is now, I can't eliminate these. What I have to do is I have to multiply one of these equations by negative 1. So I'm going to multiply this top equation by negative 1 here. And that's going to give me negative 4x minus y equals negative 18. And the bottom one's going to stay the exact same. So now, when I add these together, we get 7x. The y's we know will cancel. And 53 minus 18 is 35. All right? So now we can go ahead and solve for x. We divide both sides by 7, and we figure out that x is equal to 5. So we can verify this is true because, again, we did this problem earlier. We know our answer should be x is 5. Well, now that I know x is 5, I can come back up here to either one of my equations in 2 variables, and I can plug in 5 for x and see what the answer is going to be for y. So let's just use this first one here. So I'm going to take the 4x plus y equals 18, and we said that x is equal to 5. So 4 times 5 plus y equals 18. So 20 plus y equals 18. And then when I subtract 20 on both sides, we see that y is equal to negative 2. And again, if we go back up here, that is what we expect our answer to be. So now that I know that x is equal to 5 and y is equal to negative 2, I can take any one of my 3 initial equations and I can plug in 5 for x and I can plug in negative 2 for y. So I'm going to take the last equation that we have. My last equation was x plus 2y minus z equals negative 2. I'm just pulling from that last equation that we had. And I'm going to replace the x with a 5 and we're going to replace the y with a -2. Again, we're solving for z here. So 5 minus 4 minus z equals -2. We know that 5 minus 4 is 1, so 1 minus z equals -2. If we subtract 1 on both sides, now we have -z equals -3. And of course, if -z equals -3, then positive z equals +3. So if we go back up to our expected answer, we know z is in fact 3, so we know we did this correctly. And you can verify your answer always by plugging in x, y, and z to all three equations. And if all three equations hold true, you know you did the problem correctly. All right? So again, just to recap what we did, these problems do take a little more time, so you have to be patient with them. There's not going to be a lot of questions in the packet, but there are, again, they do take a while to get through. So again, first step is you get to pick a variable that's easiest to eliminate. So you can choose to get rid of the z's, or the y's, or the x's, whichever you think is easiest. Once you have chosen that, you're going to use elimination twice, right? We did it once with the red. I chose the second and third equations and got rid of z, and then I chose the first and second equations, and I used elimination to get rid of z as well. Then, step 3, solve this system in two variables, right? We had these red and green equations, and we solved this system using elimination right here. Once we did that, we found x, and then we had to plug in x to find y, and then we had to plug in x and y to find z. And once we did that, we found that our answer should be 5, -2, 3. All right, so all your answers, remember, we don't have an ordered pair anymore, x, y. We now have an ordered triple, x, y, z. All right, if you ever end up with a statement that is false, like if you get 0 equals 3, that's false, then you'd have no solution. And if you ever end up with a true statement like 0 equals 0, that would be infinite solutions, all right? So most often you're going to get one solution here because we're just trying to practice this, but you could end up with situations where there's no solution or infinite solutions, all right? Those are possibilities as well.